Hey, welcome back. It's been crazy, I know. This is 6.1. We're going to talk about the introduction to linear regression. If you want to follow along, open up your workbooks and you can see what I'm doing there. Cool? All right, let's get into it. First off, if you come to page, let's see, what is this? Page 216. If you have a workbook, then you'll see 6-1 Introduction to Linear Regression, getting started. All right, cool. So there's a lot of information here in this particular section. However, 6-1, this information, it can be really summed up pretty nicely. And so when you see this stuff on a test, there's a few conceptual questions, but mostly like the 4-step process is really simple in that we give you a lot of the information. So let's get into the concepts first, and then we'll work our way from there. And this is an investigation of relationships between two or more quantitative variables. So keep that in mind, right? Quantitative variables. So we've got two quantitative variables. We'll have some quantitative variables on this axis and some quantitative variable on the y-axis. All right. Now, you're familiar probably with x and y axis from algebra, and this is really similar to that. That's why I think people have an easy time with this particular section. All right. So what we do in this information is we're really building a scatter plot, and the scatter plot is going to be different x, y coordinate values all over our graph. We're going to describe these scatter plots by form, direction, and strength. More often than not, in this particular section, form is going to be something that's slightly linear, right? And by linear, we mean if I were to fit a line in that data that's sort of a best fit line, then in this case, it's a linear form. The direction for this particular graph I've drawn here is positive. Hopefully you remember that slope when it goes up like this. When it goes up every time it goes over, then that is a positive slope. If it were to go down, then it's a negative slope. And maybe you remember if it's straight across, that was constant. Okay, so just some stuff from algebra. Strength will have everything to do with how well those dots fit around that particular line. So you'll notice in these pictures over here, this is really not very good linear relationship, but you could probably draw a line through there. In the second one, I could draw a line through there. And you'll notice the difference, right, is that these dots in this particular graph here are a lot closer to the line than these dots in this first graph. So the strength relative is stronger in the second graph, has a stronger strength than this one. This is a more moderate strength. This particular graph here on the third, that's not linear at all. In fact, it's got nothing to do with any form. If you'll notice, like, I couldn't draw a line going any particular direction that would make sense for that data, right? So this one has no form. All right, this fourth one here, it does have a form to it, but it's something like that. And so this is not linear. So we're really going to have two types of forms to talk about in this section. We'll have linear and non-linears. Okay, so we won't actually do any kind of regression with these non-linear. Right? There is things that you could do in future courses, or if you decided to take them, but they're not in this course. All right, so I'll let you read through some of those things. Let's get into, so I basically talked to up here. Let's get into this correlation coefficient R. It measures the strength and direction of a linear relationship. Let's call that G1. GI. G1. All right. G1 has a particular strength to it. And remember I said it was moderate, but there's an actual R value that better defines what that is, right? So we'll see down in a little bit that 0.47 is actually in the moderate category, whereas 0.76, which is closer to 1, has a little bit stronger relationship. So you might be able to tell, right? Let's ignore the negative for just a second. Well, not ignore it. The negative is the negative slope, and the positive here is the positive slope. But the actual absolute value of R is 0.76, and the absolute value of this R is 0.47. So this 0.76 is closer to 1. In fact, if you were to have a graph that was where the lines were exactly on, sorry, that wasn't very on, but if you were to have it on the line all the way, then this R is going to be 1. Okay, so this one here you can see is close to 0, which means there is no linear form there, and one that is exactly on the line is equal to 1. And so you'll see that in these sentences here, right? Strong positive linear relationship, and a value close to -1 indicates a strong negative linear relationship, and a value close to 0 means no linear relationship. Exactly what I just said. Cool. Next. All right. I'll let you read through those extra points. Let's get into this. All right. Now, I mentioned before that there was a best fit line. However, there's an actual formula to this, and an actual technical phrase for it is this least squares regression line. And it is the line through the data points with the smallest total of the squared vertical distances. All right, what is the vertical distances? Well, if we look over here at this particular graph, you'll see these little dotted lines, right? And if we take these dotted lines, let's say that we're taking this distance, and this distance is, let's say A prime, and this distance is C prime, and this is B prime, D prime, E prime, and F prime. And we were to take those A prime and we squared it, and we added that to B prime, squared it, and so forth, all the way to F prime. And we squared that distance, and we sum them all up, it would equal some number. And so what we're trying to do is minimize this number. Now, in order to kind of understand it a little better, let's say instead we picked a line that went like this, right? It doesn't even go near the points. I mean, it goes near C, I guess, but the rest of it doesn't go through. So let's erase all those points. And our new one would be, let's do a, oh no. Oh, come on now. There we go. We're going to do a different color. So let's say we did A all the way to the line, C to the line, B to the line, D to the line, E to the line, F to the line. All right. And we took all those, so that would be A prime. This is our new one, right? A prime all the way to F prime. And we squared all those, added them up all the way to F prime. All right. And we came up with a new number. I think without really going into any sort of proof, you could see that this number would be a lot larger than this number here, right? So this number would be larger than that number, and so there is a sweet spot, right? We could keep moving that line up until we get to this point here, and then what if we went a little higher or even higher? There is a nice sweet spot, and it happens to be this one right here, where this number, after calculating all these distances and summing them up, is the smallest, and that is where that line is going to best fit. All right, hopefully that made sense. There's a lot of information with that, but mainly we want you to get the qualitative concept that, let's erase all that, that this is, right here, the best fit line, and it's going to give us the smallest amount of deviation from the actual points. Okay? All right. Great. So let's get into some Preclass problems. First off, before we get into Excel, I'm going to show you some Excel stuff, and it's really easy this time. Really easy and also really fast. But before we do, let's talk a little bit about the the problem numbers here that we have. So, number 1, the explanatory or independent variable, and number 2, the response or dependent variable. All right, so let's get into this. I didn't really explain those yet, but this is basically just like algebra. In fact, if we think about it this way, and here's our graph again, then here's our x-axis and our y-axis. Now, the x-axis is always, in algebra world, the independent variable. And in statistics, this is the explanatory variable. So these are variables. Now, again, this one's for algebra. This one is for statistics. This is the one that we're going to end up using when we're explaining the x-axis. Okay, so this is our stat way of saying the same thing that you already knew. For y, we have something similar. This was the, did I say? Yeah, okay, cool. This is our dependent variable. And in statistics world, this is our response variable. Okay, so this is the term that we're going to use in this course for the y-axis. Now, if you think about it, explanatory and response actually makes more sense than independent and dependent, but that's all right. And the reason why it makes more sense is because whatever's on the x-axis is the thing that will explain the thing that's on the y-axis. Or you could think about it as the thing on the y-axis is going to respond to changes in the x-axis. So when we're looking at these two columns over here, you have a temperature and a mortality index. And I think everybody would agree that temperature is not going to change based on how, the mortality index changes. But the mortality index might change based on the temperature. So since that's the case, the temperature is going to be on the x-axis, and it is going to explain, or at least partially explain, the mortality index. That will be your response variable. All right, so let's go back down here. Number 1, the explanatory or independent variable is the temp. The response or dependent variable is the mortality index. All right, choose both. Oh, once again, you have all these solutions already, so you could probably just look at this on your own if you don't care to listen through this part. But that's okay. It won't hurt my feelings because I probably won't even know. So choose one. Both of these variables are, well, we set it up in the very beginning that they're both quantitative. Number 4, circle the point, 50, 100.4. This is, like I said, this is basic algebra stuff. Remember, this is the x and this is the y. So 50, go up to 100.4. That is this guy right here. Right. All right, describe the form and direction of the data in the scatter plot. So if we look at that, and we were to try to draw a best fit line, we might come up with something like that. And the slope of that is positive. So the direction is positive. And the form, well, it's roughly linear. Okay, you either have linear, nonlinear, or no form. Okay, that's all you got. All right, so number 6, which of the following is most likely the value of the correlation coefficient for this data? All right, let's talk quickly about the direction is positive. So what we're going to do is eliminate anything that's negative. So these guys are not answers. I mentioned before that a number close to 0 means that it doesn't really represent a line very well at all. And I think this line is fairly representative of the data set. So I think we can eliminate 0.2 because that's really close to something that looks more like, where was that other one? Closer to something in between this, and this certainly is not between those two types. So we can eliminate 0.2. 0.99, now we're left between those two. And let's think of, again, if I have a line and the dots are pretty close to it, that is or they're on it, I mean, that is r equals 1. 0.99 isn't much different than 1. It's pretty darn close. And we do not have anything that looks like it's exactly on the line, right? So we can eliminate that one. And that leaves us with 0.88. And that looks about right. All right. So that was your pre-class activity work. Hopefully some of that was explained okay. Let's get into the in-class work. All right. So the very first problem, use software to find the correlation coefficient R for the data. All right, let's get into Excel. So we're going to pull this up over here. And I've already placed the data in here. And so what we have, to find the correlation for a set of data like this, we're going to say equals CORREL, parentheses. You'll notice here it says array 1 and array 2. So array 1, doesn't matter which one we pick. We just need to make sure we pick the other one for array 2. Close the parentheses, and it gives us a number, 0.8749. And if you think about it, right, that is fairly close to what we found in number 6, right here, 0.88. Okay, it's not exact, but it's close. All right, so using software, though, we got an exact number, 0.8749. Right on. Use the obtained R value in guidance to fill in the blank. So 0.8749 is somewhere between here, so the relationship is strong. All right, the relationship between mean and mortality, or mean temperature and mortality, is positive, linear, and strong. Okay. Next, we have, if we had for the entire population, there is a population regression line, and they give us the formula here. And you'll notice, right, that it's very similar to something that you've seen in the past, y equals mx plus b, where m was slope, b was the y-intercept. All right. So what we have for this particular one, though, is that beta sub 1 is the one that would be the slope, because it's the one next to x. So we're going to say represents the slope. And b sub 0, which is sitting here, is representative of the y-intercept. Now, it'd be great if that's all you had to write for these, but you got to remember that this is in relation to the population. So we'll say population slope and population y-intercept. This epsilon, let's go ahead and not worry about it too much. It's very well, I'll just say this, epsilon is very often used for some arbitrary error. Okay, we use that a lot in mathematics. So it's just some weird value that we are just not going to worry about. But you don't even need to worry about it in this course. So if you'd like to drop that out of your brain, go for it. All right, number 3 is very similar to number 2, except this time we're talking about samples. And so you can see the formula is just slightly different. We're actually using a little b. So b sub 1, little b sub 1 is representative of the slope again. But again, this is not population. This is sample. And b naught represents the sample standard. Why did I write that? Silly me. The sample y-intercept. All right. Great. So let's get back to the software again. And now I'm going to show you something new. Again, grab all this data, make sure you've highlighted all that stuff, and then we're going to insert, and over here you're going to look for the scatter plot. Right? And so when we look at the scatter plot, it really looks similar to the one that we had in the workbook. To get the equation, you just click on any point, just one tiny little click on any of those points, and then right click, and you'll see down here, add trend line. Go ahead and click that add trend line, and somewhere mine pops up over here. You want to make sure that linear is selected, none of these other ones, but linear. And then down here, you'll say display equation. I'm also going to click this display r squared, just so I can show you something. But the equation is that first line right there. Y equals 2.3577x minus 21.795. That is the equation that you're going to put in the workbook. Before we go back to the workbook, though, I want to talk about this r squared. This r squared, if it's a little easier to see it this way, is a little r squared. And so if we were to see that formula, we're really taking this value that we got for r and we are squaring it. And that gives us 0.7654. And that is the number that you have here. Okay, so you can always check to make sure that you've done the right selections for your trend line, and then you'll know that you have the right equation if this r square matches up with the r square you came up with doing this simple calculation with the correlation. Right? So it's kind of a nice little check to make sure you're doing things correctly. Let's bring this equation into our workbook. So coming back to the workbook, it says use software to find the equation, and we did. And it's going to be y hat equals 2.3577x minus 21.795. That is your equation. Okay, right on. So in order to answer 5a, what is the slope of the least squares regression line for this data? Well, the slope is the thing next to the x. So we could say 2.3577. What does y represent in the least squares regression equation? Well, what does it? What does it? Well, we have to come all the way back up here and look at what we did for the in-class activity. Now, I wrote it up above, but this was temperature, right? This was the x, and the y was the mortality index. So, come back to 5b, y represents the mortality index, and x represents temperature, or average temperature. D, how much does the mortality rate increase for each unit increase in mean temperature? All right, so this seems like a trick question. It's really just this number. So I would say 2.3577, and depends on what you're talking about. We'll just write units. Okay. All right. And let's see, what was that? Slope of regression, cool. I'm going to let you work through the rest of these. Certainly send me questions. You have the solutions already. Pay attention to extrapolation. Number 8. What does that mean for these problems? Why do we care about it? Understand the definition of residual. That's important. And then finally, number 10 is a really important one for, I know this comes on the exam, and even on the final exam, but a lot of times we'll ask you, well, what does r squared mean in the context of this problem? And you will have to give this information. All right, so we already have the answer here for this particular problem. But what we're looking at is r squared is the percent of variation, and in this particular problem, r squared is 0.22. So that's where we're getting 22%, right? 22% comes from 0.22. So that's the percent of variation in the quiz scores, right? So think about that. Y, this is the quiz scores, is due to or explained by the variation in X. And in this case, X is study time. Study time and quiz scores. That is the story there. And whenever we ask you to do this, you're going to need to put these pieces together. So you've got a percentage, variation in Y, explained by variation in X. Okay? All right, the rest of this I think you guys can handle. It's definitely worth your while to work through some of these workbook problems, use those solutions to help speed that process up. Come over here to the extra tips, or extras and tips. Make sure you understand each of these pieces. And again, remember this piece because it comes up. It's such an easy problem. And if you're paying attention, you'll get it. And it's really easy. So hopefully you are paying attention. All right. So that covers 6-1. We're going to cover 6-2 on the next video. See you in the next video.